Welcome to the Regents Modern Physics problem set numbers 22 and 23 solutions. We'll get started right now with 22. Let's read and highlight important information here. A mercury atom, that tells us which energy diagram we're going to be looking at, is in an excited state. It has an energy of 4.95 electron volts. It absorbs, keyword, a photon that raises it to the next higher energy level. What is the energy of the photon? So that's E. And what is the photon's frequency? And that's F. All right, rereading the question here and using the diagram. I'll draw on this diagram. I would encourage you not to do that in your reference table. It says the mercury atom is in an excited state at 4.95 electron volts. Well, we look in the energy level diagram, and that, of course, is right there. Okay, so the electron is here, and it says it absorbs a photon. So that means photon comes in, and it absorbs that photon, raising it to the next higher energy level. And that, of course, would be there. And the next higher energy level is the 3.71 electron volts. What is the energy of the photon? They want, what's this? Energy of the photon. All right, following the rules that apply here, the only way that that photon can be absorbed is if it has the exact amount as the energy difference between the levels that the electron raised to. So, pretty easy calculation here for A. The energy of the photon is going to be 4.95 minus 3.71 electron volts. And that, of course, equals 1.24 electron volts when we subtract. In B, they want to know what is the frequency of that photon. Well, what equation relates energy and frequency? That, of course, is E equals HF. Our energy of our photon is 1.24 electron volts. And because we're using electron volts, we want to use the electron volt second form of Planck's constant, 4.14 times 10 to the negative 15 electron volt seconds times F. Divide and solve for F. Go ahead and do that on your calculator. Pause the video if you need to. And we should get 3.0 times 10 to the 14th hertz. And there's your answer. Alrighty. In 23, let's take a look at that. We read a photon with an energy of 14.0 electron volts enters a hydrogen atom, tells us which diagram we're looking at, in the ground state, and ionizes it. There's another key word. With what kinetic energy, okay, of course that's Ke, will the electron be ejected from the atom? Okay, all right, so our electron was in the ground state. So go over here and add that to the hydrogen energy level diagram. And it says a photon with an energy of 14.0 electron volts enters that in the ground state. The key to this question is that in the ground state, it requires 13.60 electron volts to ionize the atom. And it tells us that this electron gets ionized with the 14.0 electron volts. That's true because the photon had 13.60 electron volts or more. And when that happens, that ionizes the electron. In other words, it removes it from the atom. Okay? So, where does the remaining amount go? The remaining amount gets imparted to the electron in the form of kinetic energy. So the kinetic energy in this is really easy to calculate. You take the amount of energy coming in to the atom, which is a 14.0 electron volts, and you subtract how much it took to ionize it, which is 13.60 electron volts. The remaining amount gets imparted to the electron in the form of kinetic energy. Okay? All right, so we go ahead and we subtract, and we should get, of course, 0.4 electron volts of energy. And that'll do it for numbers 22 and 23. You'll have more practice with using the energy level diagrams and calculating energies and frequencies and even wavelengths if they want in the rest of the problems.